Good afternoon. I'm Karen Joyce Seidman.
I'm Peter Garred, and this is Futurescope. Injuries that have greatly affected people like Bobby Orr and Joe Namath may soon be a thing of the past. Much research has been done to develop a series of artificial ligaments with some rather encouraging results.
Today we'll also take a look at a young man who is unique in Canada. Gilles Costeau can only move his head and one thumb slightly, but thanks to computer technology, he isn't all that limited in his endeavors. We'll have more on Futurescope after this. There's no two ways about it. Wayne Gretzky is one of the greatest hockey players this country has seen, but there's no way of insuring him against injury. However, now there is a way to treat what ails hockey players the most.
Artificial ligaments may one day help to eliminate injuries that burden a person for life. Although the ligaments have only been tested on animals so far, results indicate that one day they will be used on humans. Futurescope's Jeannie Lee visited the University of Montreal, and she has this report.
To most of us, our knees are knobby but useful things in the middle of our legs. They bend when we sit, they straighten when we stand, and generally we don't think about them very much. Until something goes wrong, we don't realize that the knee is a complex structure serving as a vital connection between the two unstable calf and thigh bones. And to mechanical engineers who study the knee, it is like a link between two pieces of wood, one placed over the other.
Since 1976, a team of physicians, engineers, technicians, and graduate students of the Department of Mechanical Engineering at the University of Montreal has been studying the knee and its stability. This in response to the need in the world of biomechanics for a prosthesis or an artificial replacement for the cruciate ligament of the knee that is so often injured. The knee is an action area, an area of constant movement. The stability of this structure is naturally supported by different elements.
First, we have muscles which are located around the knee. Then there's a tendon that reaches behind the knee and runs into the quadricep muscles up here. And the most important ligaments of the knee are located here, called the cruciate ligaments, the anterior one and the posterior one, which holds the knee together. Now let's meet Professor Gilbert Drouin, who will shed more light on the problem.
We've seen that the knee is a very complex structure made of muscle, ligament, and bones. Here we have a model which shows the femur and the tibia that are linked together with ligament. Basically, we have four ligaments, two outside ligament, which are called the collateral ligament, that prevent the lateral bending of the knee on medial and lateral side. We have in the inside two other structures, which are the anterior cruciate ligament and the posterior cruciate ligament, and their role is to maintain the stability and to prevent that back and forth motion.
The knee cruciate ligament is especially prone to injuries from numerous sports activities, namely skiing and hockey. Because it cannot repair itself like bones or muscles can, it often needs reconstructive surgery using living tissues like tendons.
Due to the limited success of those reconstruction, over a long time period, we were faced with the problem of the need of another tool, and we're using or developing a new concept here, the cruciate ligament prosthesis. Basically, the ligament here is a very well-made structure and very complex in its behavior. And it's not that easy to replace that structure that evolved over millions of years.
This opened the door to experimentation with animals, namely canines. This traction machine determines the characteristics of natural ligaments. Besides having a rupture load as high or even higher than the natural ligament, a prosthesis should behave as closely as possible, like the ligament in normal activities. Therefore, 38 canine ligaments were tested and were found to behave mostly like springs. The spring idea was first put to use as early as 1978. This machine, entirely conceived and built by the research group, gave birth to the first prototypes. The main concern was to find biomaterials that would neither break nor deform under normal loads. The other was to determine the right angle of the winding of the biomaterial. Soon everybody felt ready to try the implantation on canine knees. A new concept was proposed.
Basically, the prosthesis is made of 3 parts. 2 metal attachments, a central core, and fibers that are wrapped around the core, as can be seen here. The concept is the more you pull on the prosthesis, the more you're going to squeeze the soft core material. And therefore, you can obtain the same spring behavior as the ligament.
Holes must be drilled into the knee before the prosthesis can be anchored by screws inside the bone. Thereafter, a second machine was built to produce the canine prosthesis. The miniature winding machine was specially designed to spin the fibers around the small core and the pulling stem at the estimated angle. For a medium-sized dog, the active part of the prosthesis had to be 17 millimeters long and 4 millimeters in diameter. 2 experimental models were built. These were tested under tension to verify the theoretical results. For both devices, the core is made of silicone rubber and the fibers are of Tevdek, which is composed of Dacron, polyester, and Kevlar. Results show that the proposed concept can very well duplicate the behavior of the dog's ligament. Furthermore, the same concept could equally be used for the replacement of the anterior cruciate ligament in humans. At the Hotel Dieu Hospital of Montreal, we are now ready for the big test. The 2 physicians are going to implant the prosthesis to replace the canine stifle joint ligament. It is a delicate 2-hour operation requiring sophisticated tools, some especially designed by the research group. The prosthesis needs to be put at the very same point the natural ligament was.
Okay. Okay.
After 9 weeks, the dog was put to sleep and his knee was examined at the laboratory of the Polytechnical School. The prosthesis was found to be broken. The engineers discovered that the prosthesis was not only facing elongation forces while in action, but also torsion and flexion ones. 2 fundamental problems had arisen. First, the need of an improved prosthesis, and second, the desire to not sacrifice dogs without good results. They went on and invented this testing machine. It can mechanically reproduce all the forces to which the ligament is submitted. Here we can see a new design. The prosthesis will be covered by a girdle that will give it more strength and resistance. While that new concept is being developed, the engineers are still looking for improvement.
Cette machine reprend les mêmes principes que la précédente
Paul Gilles is presenting the latest invention, a new testing machine allowing 5 prostheses to be placed and tested at the same time. Now all 5 can be simultaneously subject to the forces at variable strength and speed. Some electronic devices have been placed onto these attached parts so that results are kept in time memory. In 48 hours, a year's cycle of activity can be estimated, and the worst forces would have been applied. After successful tests in canine implantations, the next step will be human implantation, estimated by engineers to be in 1984. Meanwhile, the research group will not be idle. Already a number of other projects are underway. For example, the study of the cruciate ligament will be expanded to one of the entire knee.
At the same time as they are giving more hope to those with knee injuries, specialists here at the École Polytechnique of the University of Montreal are contributing to the progress of the entire biomechanical field. For Futurescope, I'm Jeannie Lee.
Engineering and medicine are now working together, combining both fields of knowledge in a unique application. A fine example of how traditional disciplines in science are now able to solve problems that separately could not have been solved. This reflects a new trend in scientific research, integrating new discoveries and ideas for more adequate solutions to problems in medicine. The artificial ligament is only one of the projects now being studied today, and studies are growing rapidly. Next on Futurescope, an interview with a man devoting his life to this type of research.
Joining me now is Gilbert Drouin, who is a professor at École Polytechnique and research director at the Montreal Rehabilitation Institute. Welcome at Futurescope. Okay, now our first question is, why are mechanical engineers involving themselves in orthopedics?
As a mechanical engineering professor, I've always been interested in design, and I thought that the area of medical application would be a very profitable one. So I decided to take on a PhD in biomedical engineering, and then at my return at the École Polytechnique, I got more involved in this area.
Mm-hmm. And how did orthopedics and mechanical engineers get involved together?
It started from a need that was experienced by one of the surgeons in Montreal here, Dr. Drouin, that has been working on the area of the cruciate ligament for a few years. And he thought that the association of engineering and medicine would be very profitable. So he came to École Polytechnique, and we thought the problem was very challenging at the time and very interesting, and we still think it is.
That's good.
And the project started and evolved, and with it the team grew up, and right now we have a multidisciplinary approach where medical people and engineers are working together. The engineer, for instance, are mechanical engineer, metallurgy. We have some people in physiology. We have technical people from electronics, mechanics, and physiology, biology, naturally the graduate student, and so on. So it forms a very interesting team.
What has been the evolution of that orientation?
From the beginning of that project, we started with a very narrow problem, which was, prosthesis. And soon we found out that we needed to have, more and more people. And the way we grew up is we tried to solve the problem as they present themselves. So the more discipline got involved into it. And now, as you've seen in the film, we have activities at the École Polytechnique and also at the Hôtel Dieu Hospital. And we foresee that, there's a lot more work to be done, and that this approach that has been taken for the multidisciplinary and the team approach is one better way of solving these problems, because you can tackle a lot of facets at the same time, and you can integrate that knowledge. In other words, the Leonardo da Vinci, the universality that he had cannot be found in one man now. We have to find it in one team so that we can integrate all that knowledge.
I believe we have a slide here, and then you're going to discuss some future projects and point out some things for us.
Yeah, from the start, the ligament itself is one part of the knee, and it is very, the ligament itself is complex, but its function in the knee is also very complex. So we found that we had to go into the modeling on the knee. And the slide that you see there, in the center part, you have the model of the knee. This is maybe a particular model because it's a computer model where all the information that we get from different studies are integrated in there and somehow put into numbers. And to do this in a good way, we have to find the characteristic of the material itself. That's what you have on the top of the slides there, where you have the characterization of the material, both microscopic and microscopic. And then we need to find data on anatomy. And there we need to have numbers like dimensions, size, and so on. And then everything has to be integrated to understand a little better about how the prosthesis should behave.
Now, you're involved in some other research, aren't you? And you're going to tell us very briefly about that. We're running out of time.
Yeah, last year I became director of research at the Rehab Institute, and there was a project going on there made by, or Dr. Lozak, Mr. Lozak was working on this project that involves a new area where computer get involved, and it is a very interesting and I think promising area.
Okay, well, I'd like to thank you for being here and taking the time. Many handicapped people rely on mechanical gadgets to aid them in everyday routines. But what distinguishes Gilles Costeau is that his support hardware is computer controlled. He has access to a telephone, intercom, radio, lights, tape recorder, and any other conveniences we fill our homes with. And he has access to them all at the push of a button. Futurescope's Marisa Tonieri visited the Notre-Dame de la Merci Hospital, where she talked to this remarkable young man whose advantages are few, but whose accomplishments outnumber most people's. And she has this report.
Gilles Costeau is a University of Montreal student pursuing a master's degree in philosophy. Like a growing number of students, the use of a home computer has entered his daily routine. And like many students, Gilles has found that computer language is a language well worth knowing. But unlike most students, Gilles is a quadriplegic, and the new computer technology plays a far more crucial role in his life than in others.
Ça, l'informatique peut lui donner cette liberté d'action-là. D'après moi, c'est de plus en plus indispensable. J'étais au début de mon baccalauréat à l'Université de Montréal. C'était ma mère qui a dû mes travaux depuis le collégial. Puis à l'université, ben, commençait à trouver ça plus difficile. Alors j'ai pensé que l'informatique pouvait devenir un moyen de travail absolument fantastique.
For Gilles, who has movement of his head and right thumb, the computer allows him to do tasks that would normally be impossible. Holding a balanced tone arm in his mouth, Gilles punches instructions on this keyboard, which controls his Apple II Plus computer. The Apple itself is connected to other equipment in Gilles' room at Montreal's Notre-Dame de la Merci Hospital. Gilles hopes to incorporate all his equipment into the main Apple and then streamlining the entire system to make it more portable. He also hopes for a voice-activated computer which would help many handicapped people by making operation much easier. Meanwhile, the system, Quebec's first, is still pretty handy. Work can be written on it and later be called up. For Gilles, who is writing and editing his master's thesis on the dilemma between public and private life, this can be invaluable. If computers become part of every handicapped person's home, it would be, at least partly, thanks to Gilles. He approached the Handicap Board of Quebec with an idea of computer-operated aids to the handicapped. The National Research Council and the Montreal Rehabilitation Institute also helped in the design. And to know his system better, Gilles took some computer science lessons from a fellow University of Montreal student. This new computerized arm enables Gilles to easily turn the pages of any book he reads. Surely a useful tool for a university student. Gilles sees the use of a computer as increasing the independence of handicapped people.
Bon, l'ordinateur, en plus de travailler, pour quelqu'un qui vit à domicile, par exemple, ça lui permet d'ouvrir ses portes, d'ouvrir ses fenêtres, d'allumer la lumière, la télévision, de répondre à la porte, au téléphone.
Est-ce que ce système est simple? Est-ce que tous peuvent y adhérer? Tout le monde pourrait avoir accès à un tel ordinateur où il faut des connaissances en informatique?
Il ne faut pas nécessairement des connaissances en informatique. Quelqu'un qui sait opérer son ordinateur peut avoir beaucoup de plaisir à travailler avec. Mais quand on a des connaissances en informatique, ça permet, au fur et à mesure que l'on découvre ses besoins, de les résoudre soi-même.
With the setup in his room, activities most of us take for granted as effortless are now simple for Gilles, such as making telephone calls.
Moi, qu'est-ce que je viens de faire? Là, je viens de faire toutes mes boîtes à fleurs. Et il fait du soleil, vous autres, là?
The radio can be switched on without calling someone else to do it. Once started, Gilles is not about to stop. His constant goal is to make computer companies aware of the needs for portable systems for the handicapped. Gilles Costeau's computer has done what computers are designed for, and that is to help. The work Gilles put in developing his system has paid off with a greater independence for himself and perhaps for many others in the years to come. I'm Marisa Tanieri reporting for Futurescope.
Eventually, through the use of a computer as a central control device, Gilles will be able to operate his hardware from a small, voice-activated box that can be mounted to his wheelchair. This will eliminate cumbersome separate switching components. The increased sophistication of command systems will enable Gilles to have a greater degree of control over his environment with less effort than ever before. So when people say computers are taking over and dehumanizing society, think twice before agreeing. They can do an awful lot of good. An electric car? You probably have an image of a little golf cart type contraption scurrying around and maybe not making it past the 11th hole.
Marathon Electric Vehicles has developed a 6-wheel machine capable of traveling 80 kilometers per hour over a distance of 60 kilometers. At the end of the trip, it plugs into a 220-volt current. I'm Peter Garred.
I'm Joyce Seidman. We hope you'll join us again on Futurescope.